everyone and welcome to this Art channel. It's time to make experiments. Today we are going to make experiments with PD and PID controllers and try to understand which controller is better. Some of them have advantages and disadvantages. We are going to understand all of them, so let's not lose time and finally start.
Before we start our experiments, I would like to show you how can you make a configuration for Hello box so that it will work properly. You need to open settings, that's what I've done a moment ago, and you can see this yellow screen to make some configurations. Actually, all the steps are written here, but let's make it together. So step number one, we need to choose serial receiver. Let's make it. And from instrument control toolbox, choose it please. Then connect it to one and choose your port. My port is 3 and data type is unit 32. Then block sample time should be 0.05 and then I click OK. Then we get this serial configuration box after we click OK, but it says that baud rate must be 100,000, 15,200, but ours is only 9,600, so it won't work properly. For this reason, I just delete it and make one more serial configuration. And I again choose a port here first, COM3, and put my baud rate to this value. Now it must work. Let's save it and start our lab. After we made our configurations, let's finally start with P controller lab, and what we need to do to say that we choose ports 3 here and press labs. Choose lab 2 and click lab 2 model. Okay, now it's opened and we don't have any model here because we need to make it by ourselves. So the first thing for P controller, what we need is the gain block. Let's put gain here and connect it to the DC motor plant. Let's add sum operator to here, but don't forget to double click and change one of the sign to minus to make a feedback. Then we connect the reference with the reference and also our unit step function with the gain, and we make a feedback here. Let's also maybe make a scope, but I'm not sure if we really need it, but let's just put it in case. Then we need to put the value of 400 RPM, sample time 0.05, and analysis screen is right here. So let's check. And we write here 10 seconds and click run. So what we can see, by the way, here is the box. I'm not sure if you can see it right now, but I will put the video. Approximately it reached the reference, so it became 400 RPM, but as you can see the function is a little bit like this. So let's open the simulation data inspector to analyze it better. We reached our reference, but it's something like 350 RPM, and it was going back and forth. Maybe we need to use a higher controller. No, maybe let's do it too, because it's a proportional controller. Then I click run here again. Let's open our graph, and what we can see, the blue line, you remember our previous run with the P controller value 1 and now value 2, it will be red color. And what we can see, yes, we reached 400, but the oscillations is also bigger. So that's the problem of P controller. If you make it too small, it doesn't achieve the desired reference. If you make it too big, it makes very big oscillation. To test iController, what I need to do just to change my model, I just need to put integrator to here. Integrator. So yeah, it's in the Laplace form, don't forget it. And I put my integrator to here. And this time I have the reference, let's say 200 maybe, not 4, and let's run it. Well, this time, as I can see, it rotates like better. It doesn't make any oscillations nearly. If it makes very slow, but my eye can't recognize it. Well, let's wait for the final graph to analyze it. And yes, as you can see, even from this small graph, the oscillations aren't that big. The rise time is actually very short here. The overshoot isn't that big, less than maybe 210 RPM. The overshoot isn't that big, and it goes like nearly with no oscillations. If I increase the value of eye controller and make it 8, for example, let's also check it. Achieves our reference faster than first controller of value 1, but it has a greater overshoot, and then it has some oscillations, but still it settles and we nearly have no error. Well, that's maybe the problem of eye controller. If you want to achieve rise time faster, then if you want to achieve the reference faster, then you need to pay with overshoot. We have two controllers, P and I. If P controller have an advantage over something, then it has some certain disadvantages. But these disadvantages could be fixed with I controller, and why not to combine them together? For this reason, I again open my model and add one more controller to here, just a gain controller. How can we combine all of these things? I just put one gain block to my old model to here, and one more sum operator to here, but this time I don't change the signs. I remove this connection, put a sum here, and connect maybe my I controller, connect my P controller, and connect it to the power plant, and at the same time I connect my P controller to here. And give a reference 400 RPM. Oh, we see that it achieved exactly 400, no oscillations, the overshoot isn't that big, but we are going to check it. Okay, you can see, right, that we achieved the 400 value. We achieve it in a very short time and with a very small oscillations. By the way, I rearranged my graphs here. I give them the name, so now you can understand better. And let's give the name to the last controller too. It has an orange color and it will be PI1, let's say, the value of I controller. So let me close other controllers for now. What can we see? We have some like rising time very much shorter than the previous one, and it directly achieves the 400 RPM and oscillates very slightly. So I will make a PID controller, and let me replace the integrated function with the derivative function here and insert it like this. Oh guys, it oscillates too much right now with PID controller. I don't like it. With the I controller it works much better. Let's check what's going on here, and you can see the orange is PI controller and the green is PD controller. Well, what can I say? That it definitely works worse. It achieves the reference faster, but it starts oscillating. Okay, let me add an integrator to make all of our oscillations much smoother. And we need an integrator for this, and also the gain operator. I really, yes, well, that's what we expected. It works very smooth. The reference is 400.
So, from our experiments, what we could understand that P controller, even though it helps us to achieve the reference, isn't that good. Because the low value of P controller doesn't achieve the reference, but it doesn't have any oscillations. The high value of P controller achieves the reference but has lots of oscillations. That is completely not good for the system. Well, what about iController? iController is nice, but it achieves the reference slower than pController. Well, if we increase the value of iController, then it has an overshoot. That is also a problem. Then we combine PID controller, and what did we get? Well, I didn't like it because, yeah, we got the reference directly, but again we have these oscillations. Then we combined P and I controller, and we got a smooth, a very nice function that I like it. We achieved the reference. We nearly had no oscillations. And then we combined PID controllers, and it became the best because it was very smooth like PI controller, but at the same time the oscillations were even smaller.